Welcome to another episode of the Melbourne Athletic Development Podcast. This episode, as always, is brought to you by the support of Strength by Numbers. Strength by Numbers have created an integrated clinical and sports performance system. The AXIT system uses force platforms, dynamometry and strain gauges to objectively measure everything from isolated movements to sports performance tasks. The system has greatly enhanced our clinical practice, decision-making and objectivity. We are no longer guessing. The greatest thing is its ease of use both for practitioners and clients. There are no wires, no fixed setup. It's a fully integrated Bluetooth system. If this sounds like something that would enhance your practice, visit strengthbynumbers.com and tell them that Melbourne Athletic Development sent you.
So today we're very honoured to have Emeritus Professor Uwe Proske with us. And so to start the conversation, do you want to give us a background of who you are, Uwe, to give some context to the conversation?
I began my academic career at Monash. I originally graduated from Adelaide, but I began my professional career at Monash, and I've been at Monash 50 years or something. And I worked my way through the ranks and finished up as a professor, as a personal chair, and retired back in 2008. And I've been lucky enough to be able to continue to have some research interests ever since, right up to the present time. And I've really very much enjoyed it.
What was your research in, Uwe?
My background training is in zoology and botany, but I became interested in physiology, and I moved into the physiology department at Monash. My supervisor was a physiologist. I was interested in understanding how the body works, and I tended to do it from a kind of selfish point of view. I wanted to know how
Don't we all?
Well, how I worked, what made things go as they do, and I fairly quickly became seriously interested in the nervous system, particularly the sensory side of the nervous system.
That's the more interesting side, I think.
And often the forgotten side, I think, too.
The motor side, really, in my mind, is equally important, but the chap I was working for was a sensory physiologist, and it didn't take long for me to become fascinated by sensory things. And I've always taken quite a broad view. I mean, in the last, 30 years, I've been working almost exclusively on people, with people. But prior to that, I looked at sensory receptors in all kinds of animals. We looked at electroreceptors in the platypus and the echidna. We looked at muscle receptors in reptiles, a whole variety of things, infrared receptors.
Is it a hard transition going from zoology to physiology for humans, or is it very much the same sort of process?
Well, if you go into a physiology department, traditionally a significant number of the staff are medically qualified.
Yeah.
So
does that create barriers in terms of how they
potential barriers, and you just have to be on your toes and catch up very quickly. But I loved physiology. I found it fascinating, and not only the nervous system, which was my main focus, but even the cardiovascular and respiratory system. I always thought it was interesting, and I enjoyed. I finished up teaching some of that stuff. It was the blind leading the blind. But I enjoyed it. I enjoyed reading about it, understanding it, and then teaching it. It was terrific.
So in terms of, you said you got interested in the sensory side. What captured you? What were the things that you started to go down in terms of your research to look at from that sensory point of view?
What happened was I came to Monash as a zoologist, and my supervisor, who was medically qualified and was interested in things like proprioception.
What was their name?
Archie McIntyre. He was the foundation professor. Anyway, he said, look, muscles have got these sense organs in them. Why don't you look at muscle sense organs in animals rather than in people? And I finished up studying initially in reptiles and then quite a lot in laboratory animals, rats and cats.
Why in animals? Because of your background? Or?
Because of my background. Okay. He felt that this was a useful transition. And it worked out that way, and I became more and more a conventional physiologist over the years. And in this last 30 years or so, I really only worked with people. And It's been great.
When you started looking at sensory organs in animals and then transitioning to humans, were there some significant differences in the anatomy of looking at reptiles compared to, say, mammals and specifically humans, and even the organisation of sensory organs within the human system?
Yeah. And in response to your question, I do have a continuing deep interest in evolution. And
you have to, don't you?
Well, it's not a matter of have to. I want to. I am what I am, and this is to do with where I came from. And the guy who recently got the Nobel Prize on the genetic code in Neanderthal man. It's just fascinating. It's a concept that's constantly in my mind, and you're right. The reptilian muscle receptors, which was my subject, are very different in a number of respects. More primitive, using the word with caution. A very small, fascinating point that's emerged recently is that the reptilian and also amphibian muscle spindles don't have a fusiomotor supply, which is their private motor supply to make the sense or the spindle contract, which means it changes its sensitivity.
As in like the intrafusal fibres, are you referring to specifically?
Yeah, that's correct.
Yeah, okay.
So reptilian and amphibian spindles don't have a fusiomotor supply. In other words, a facility for regulating the sensitivity of the receptor. We have, and what just emerged just recently is that birds do that as well. Birds are far more highly evolved than we give them credit for, and I just thought it was an interesting point.
And what, in terms of, say, for our listeners, what does that allow us and potentially the birds to be able to do?
Big question.
Compared to, say, a reptilian or amphibian tissue.
I mean, a bird's a good example. If you look at a bird moving about and flying and what they do in flight, their motor control is vastly superior to that of a lizard paddling about in the bush. It's an order of magnitude more subtle and sophisticated.
And has it got to do with that dexterity?
That's correct. Yeah. That's correct. And that's true in us as well, in primates. I mean, all mammals have got a fusiomotor supply.
Is that less so in than, say, chickens, for instance? Because chickens are typically not such a flight, or don't fly as much as other bird species. Because one thing that I've, from my understanding, this is actually some of the research done from Carla Stecco. I'm not sure if you've heard of her. She's a professor of anatomy at the University of Padova in Italy. And if you look at, say, a chicken, one thing that you see is the development of their sensory motor system is less evolved than, say, humans. And part of that is because of the lack of the fascial network within a chicken. And from what I understand, most of these sensory mechanoreceptors are found within the fascia itself, like within the peri or epimysium. And so if you think of a chicken, its ability to control fine movement is very limited. And you can even see that when they walk, for instance, where as they walk, their head keeps moving around quite rapidly, as opposed to humans, where we've actually developed a very good ability to change direction, but still maintain good head position, which is obviously very important for our exteroceptive senses, particularly vision.
I agree with all that, but a chicken, in a way, is an unfair choice because, they're all in sheds or in contained enclosures and their movements are restricted and they're... But, if you watch a flying bird like a swallow, it's breathtaking. Yeah, absolutely. So they're pretty good.
Do you see that though too, or just out of interest of thinking about the fascia's involvement in the sensory motor system? And
you asked a question about that.
Something I'm interested to hear your thoughts on.
The only way I can respond is by describing to you what the muscle spindle is like. So it's a bundle of muscle fibres that are smaller than the ordinary muscle fibres, and the spindle lies squeezed in between the ordinary muscle fibres. They lie alongside, parallel to the ordinary fibres. Their location's often not very far away from the nerve supply to the muscle. So where the nerve goes in, often also the blood vessels go in and the spindles are nearby, but they are scattered through a large part of the muscle. And a muscle like our biceps brachii would have, 50 to 100 spindles, so quite a sophisticated sensory apparatus all within this one muscle. The way the spindles work, you're quite right, the ends of those small intrafusal fibres attach to connective tissue adjacent to the ordinary muscle fibres. Now, whether it's perimysium or not, I don't know. I can't remember the details of that. The spindle itself is a spiral nerve terminal that runs around these intrafusal fibres, and when the fibres are stretched, they open these spirals, producing stretch of the membrane of the spiral, and that in turn produces impulses in the receptor. And those impulses then travel up to the brain.
And correct me if I'm wrong, from my understanding too, the function of the muscle spindle will also determine your ability to recruit the alpha motor neuron. Is that correct?
The afferents of muscle spindles are closely connected to the motor neurons. So if you follow the afferent of a muscle spindle, then a branch of the afferent goes onto the motor neuron and makes a monosynaptic connection, and that's your tendon jerk. When you tap the knee, that response is a reflex response as a result of impulse activity coming in from the muscle spindle, exciting the motor neuron. It's a very strong synapse, and it's probably that it's part of the mechanism for posture, the continuing bombardment of motor neurons, maintaining muscle tone, which of course is also regulated from the brain. But the idea of a small loop between the spindle and the motor neuron provides you with a mechanism for tone, for muscle tone.
Well, and the reason why I bring this up is I think it's something that's often neglected or forgotten about within our profession when we talk about something like motor control, where there's a very strong theme within physiotherapy of motor control of always looking at output from the brain to the periphery to contract muscles. And obviously that's a key element to it. But one thing I think seems to be forgotten about is how sensory feedback regulates motor control. It's not motor control, it's sensory motor control. And so I think the thing that's interesting to highlight here is we're constantly getting this feedback from our periphery to regulate where we are and how much tension there is within our soft tissue system, which then creates certain stretch reflexes, whether that be excitatory or inhibitory, to help regulate movement.
Just a couple of things. One is the stretch reflex is a spinal reflex. You can't stop it. If you try voluntarily, you can't stop it from happening. So it's a hardwired reflex. But spindles do lots of other things. They not only act on the motor neuron of that self-same muscle, the homonymous muscle, but they also act on synergists and antagonists. So it's a whole network of connections, and they're of different strengths. So the monosynaptic one is very powerful. There's a disynaptic inhibitory one, so there's an inhibitory interneuron in between. Anyway, we don't want to go too far there. All that stuff is reflex and, in that sense, automatic and does not access consciousness.
Well, it's really good that you bring that up, because one of the things that we talk about often in this whole sensory motor control discussion is the fact that in our world, a lot of clinicians that we're a little bit critical of try to isolate specific movements and almost separate that understanding of that reflexive pattern. And they don't understand that those reflexive patterns, as you said, have come from an evolutionary development, and they're there not only to protect us from, whether it be a danger, you touch something hot and it'll sense that and it'll change your behaviour, but also actually they can be, we work a lot in sport, we work a lot in performance. If you can access those and you know how to evoke some of those reflexive patterns, you can actually enhance someone's performance, because what you're doing is you're getting them to access, as you said, an unconscious pattern of movement that often has higher force outputs than what they can create voluntarily, and it allows for greater performance. So Jack and I have been talking about this a lot, but just the fact that if you go down this pathway that you think that you consciously have to control every single movement, not only does that often lead to discoordination, it actually doesn't achieve anywhere near the level of acuity or quality that you can achieve if you actually are using the patterns that are built into they're hardwired into our actual structure, which I think is really interesting that they're built into what we actually are as an anatomical structure.
And that's reinforced, I think, by the specificity of movement because, again, correct me if I'm wrong here, Uwe, but within the muscle spindles you have the nuclear chain and the nuclear bag fibres.
Correct.
One assesses more the change in length and the other one assesses the rate of change in length.
We can just talk about that, So the muscle spindles has really three kinds of intrafusal fibres. The dynamic nuclear bag, which is thought to be associated specifically with dynamic responsiveness. There's the static nuclear bag and the nuclear chain. Both, and there are two kinds of sensory endings, primaries and secondaries. Both primary and secondary endings do provide position information. It's only the primary endings that generate movement information. And a point that you brought up in the thing is that when people grow old, the spindles become wrapped in connective tissue to a point where the dynamic sensitivity of the primary ending is interfered with. So one of the things as we grow old that we lose is the acuity of our movement sensitivity.
Is there a way, like Jack, you probably have looked at this more, is there a way of affecting that? Is it as simple as, exposing yourself to those things?
Well, and I'm interested to hear your thoughts, Uwe, but I think one of the big things that regulates that is there is this simple process of aging, but a part of that is also based on how much are you maintaining or optimising the function of that system.
It's this old boring idea, if you don't use it, you lose it. That
but
sort
it's
of
true.
Thing. No, it is true. Obviously, if you exercise and maintain a range of motion, they will have significant effect on proprioception as well.
Well, interestingly, do you know the researcher Paul Hodges at the University
of
Queensland?
Yeah, I don't know Paul Hodges.
Okay,
so indeed.
I've been really fascinated by a lot of his research in the last 5 to 10 years and really starting to understand how motor control is influenced by sensory input. And again, he recently did a publication with, again, Carla Stecco in the University of Padova, looking at what changes happen to the connective tissue surrounding muscle spindles in response to injury. So it was an animal model where they did an intervertebral lesion and looked at changes within the erector spinae muscle. And what they noticed is that over time, you started to see more fibrotic tissue formation around the muscle spindle, which led to its dysfunction because all of a sudden the intrafusal fibres' ability to be able to sense and change the tension.
They contract in both directions and widen the central equator, which is where the spiral is. And if they can't do that, then of course it's not working. And the spirals are connected delicately to the intrafusal fibres. And anything that interferes, and of course the whole thing is in a fluid-filled capsule, and if this is all wrapped in connective tissue, then it doesn't work properly anymore.
And for me, this is where I start to think of when we see people in our situation who have got injury, when we think about the sensory motor system, one of the big principles that are used in physiotherapy is always thinking about this top-order down approach of trying to get all your motor units to recruit. And I often think, is that not the right way to approach it? Because if we're starting to get changes in our motor output, is it related to sensory input changes as well?
I'm sure.
And then that opens up the question, well, how do we actually affect that? How do we regulate that?
Just quickly back to ageing. I mean, one of the things that happens is with ageing is that there is progressive motor neuron death, and those motor neurons die. The terminals on muscle fibres degenerate, and initially, anyway, other motor neurons whose terminals are nearby send collaterals to take up these denervated fibres, but that can only go so far, and I become progressively weaker. Sometimes just trying to rotate a doorknob that's stiff, I find that quite difficult now. I never felt it before. So there is that process. sarcopenia is what that's called.
Yes.
As we grow older, and of course I'm particularly interested in that, as we grow older, there is sarcopenia, we're getting weaker. Proprioception is not quite as sharp as it used to be. That's probably to do with lack of sensitivity of the spindle as a result of the connective tissue around it. And I think also there's an influence that I don't fully understand on the sense of balance. And my sense of balance is not as good as it used to be.
Well, you've brought up the topic of proprioception. So I'm interested to hear, what is proprioception, and more importantly, why do we need it as humans?
Yes. Well, what is proprioception? Another term for it is the senses within. The proprioceptive senses include the sense of position, of limb position, where is my arm if I cannot see it, sense of position, the sense of movement, and those two are sometimes put together as the kinesthetic sense. So position and movement are bundled together, called kinesthesia. And then there's the sense of force, the sense of effort, the sense of heaviness, and the sense of balance. All those together comprise the proprioceptive senses. And one of the things that drove me was that I wanted to know about myself, how I did these things, and you know, whenever I'm lifting weights or checking my position sense, I think of these things, and it's fun to do that. It's really interesting. It's enlightening to yourself. It's one of the things that's been driving me. And another side that's not directly relevant is I tend to be driven in understanding these things by my own curiosity rather than the desire to solve clinical issues. While that is a worthwhile thing to do, it's not what's driving me. And I think it's a part of human nature to want to know how things work. And I set up experiments just trying to understand. And it's wonderful. You know, what sometimes happens is you set up a hypothesis. This is how it's going to happen. And then you do the experiment and you get exactly the opposite result.
How often does that
happen? Then you know you're on the right track. then you know you're on the right track.
Why is that? What makes you think that you know you're on the right track?
Because I asked a question and I got something that's exactly the opposite. I'm obviously touching the material, but I haven't understood it fully. And I'm only encouraged by it.
I think that's a great thing, and it's a great way of looking at not only research, but actually any professional or even personal endeavour. I always say this to patients, but I think it's relevant in everything, is the only result that I don't want is that nothing changes, because that to me is more confusing than if it gets a lot worse or it gets a lot better, I've got something to work with. And I think in research it would be very similar, where, as you said, it's actually more intriguing. Obviously, I'm sure you'd be really excited if your hypothesis gets proven to be true, at least in that instance.
Well,
that's excitement. But I guess when it's wrong, you're like, okay, where do we go now? What questions has this brought up that I hadn't actually considered before?
That's a key issue. If you do an experiment and it leads to more questions, you're doing the right thing. If you're up against a dead end, then you've got to look elsewhere. So that's really important.
It's an important question, because I think this is relevant for all clinicians, but I think it's actually just relevant for people in general. Do you think that has changed people's curiosity and want to actually take on that almost negative result? I feel like there's something interesting that's happened where people have gotten less comfortable with uncomfortable answers almost. And I feel like generations such as yours actually didn't see that as a point to stop. They saw that as you said, encouragement to ask more questions.
Incentive.
Are you noticing any difference with that, with younger researchers that you've dealt with over this last sort of 15 years?
I look at my grandsons, and you know, they are consumed by tablets and computers and things, and
they're not researching,
and everything has to be quick, and the answer has to be immediate and black and white. And that's not really how I see the world. But I'm a different generation. I shouldn't really criticise.
No, I don't think it's a criticism in any way, but I think it's an observation that there is that difference about want to have immediate information or immediate success. Do you think that... I think because this leads into another really interesting thing, and I know that you mentioned it as we were talking before this started recording about the fact that it did get harder and harder for you to access, say, funding because of the clinically driven questions that get put forward. And I always think back to the story of Crick and Watson when they were looking at DNA. I think that from what I remember, and you can correct me if you know more, that was about an 11-year process that they went through to actually get to that finding.
Yep.
And if I've heard it said a number of times, but if that was today, they would never have arrived at that point because someone would have cut their funding well before they even arrived at such a momentous observation.
Yes.
And I think that that's almost, it's a blight on where we've almost landed in terms of research, that people are researching to get grants, not to actually elucidate information that may be useful now or in maybe even the far future.
And I think tied in with that too of, and you mentioned this before, Uwe, of so much of your research is embedded in understanding the basic sciences, where we see much more of a transition to wanting to look at its applied science. And I think the other issue with that is when you're doing applied science, you typically want to see a result. You don't want to get to the end of the research where you go,
more questions.
or we go to like, oh, actually, we didn't find anything, because that's also not something that a lot of journal articles probably want to publish, I imagine.
Yes. Well, it's my impression that in the past, at least, maybe not today, but in the past, if I looked at the performance of a department that was interested in clinical matters, the scientific relevance of the material from such a department was inferior from a basic science department. When you give people a goal, you are in a sense restraining them. Yeah. Their imagination is not allowed to fully spread its wings, and that can lead to consequences. You know, people like Andrew Huxley, who could have really won 2 Nobel Prizes. He got one, and he did his work on frog muscle, and of course it's totally fundamental work. So, but I just make the point that things don't have to be clinical, and I think in a sense it's short-sighted to oblige people to want to have a clinical outcome. Let their spontaneous enthusiasm direct them. But, you know, the answer to that is it's taxpayers' money. We don't want people in ivory towers. We want them, we want them to justify their existence. But I think in the longer term, that's not a good thing.
Yeah, no, I agree with you. And I think that, as you said, it doesn't foster creativity. No. And it means that people are almost researching in fear for their next funding.
Yes.
And as I think the saying goes now is, publish or perish. And that, I think, is a real danger to the knowledge that we gain, because, as you mentioned earlier, like, curiosity is the thing that's probably going to drive most people. Yeah. And if you're not interested in the research you're doing, it's probably going to come through in the papers that you write.
It does.
Yeah. Like, I think, and again, you mentioned this earlier, but I think it's really cool. Like, you can probably explain to everyone your title of Emeritus Professor. What does that actually mean?
Well, what it means, it gives me the opportunity to continue to do research even in retirement. I'm not interested in money. I don't care whether I get paid for it or not. And in fact, I also supervise students, and I don't get anything for any of that, but I don't mind. The subject is interesting. I'm learning things, and I love being with young people because they're fresher than oldies who are set in stone, more or less, and they often bring up new ideas, and to me that's a wonderful thing. I think
it seems so rare these days too.
I think that's such a wonderful position to have, as you said, because I feel like, at least from what you're saying, that allows you to actually continue to have that curiosity without the pressure of any specific research to do.
Yes, and also I don't have the university administration, I don't have the teaching, I don't have all those things. I can sit in my little office and think about stuff, and I like it.
Well, I think the other thing too is, I feel like something that's missing from a lot of younger people's lives is having older mentors to guide them through what they do, whether that's professionally or personally. Yep. Did you have a similar mentor yourself when you were younger?
Well, Archie was my teacher, and he inspired me for sure. But a lot of this stuff is self-driven, you know. I've had lots of students, you know, PhD students and master's students, and a lot of them have stayed in the field, and I suppose that's a good indicator.
It's a positive sign, yeah.
Yeah. And they're all over the world, yeah. So in a sense, that's right. Yeah. I just wanted to say a little bit more about proprioception. One of the things that I wonder at is that these things called muscle spindles, which are in all our skeletal muscles, and our density is highest in the fingers and in the neck, these things are involved in the monosynaptic stretch reflex, they're involved in spinal reflexes of various sorts, and then they're also involved in conscious sensation. So they are a receptor with an extraordinarily broad range of functions. And I just wonder at that. It's just fascinating.
What research is currently happening? Because it sounds like you're still abreast of what's going on. And what's currently happening that's exciting you in that space?
Well, if you like, I can go into that.
Yeah, that'd be great.
I just wanted to say just a bit more about it. One of the things that Jack asked was, what were the sort of landmarks in the proprioception research area? And I wanted to answer that because it's really fascinating. And I mean, if you guys ever wanted to read any of that stuff, it's terrific. In the 1950s, everybody believed firmly, solid, close the door, throw away the key, that the sensors responsible for human position sense were in the joints. It was joint receptors that were responsible. And then a few years later, somebody began to apply a physiotherapy vibrator to the biceps muscle of one arm. The subject was blindfolded and they were told, we're going to vibrate this arm, tell us where it is. And while they're vibrating, the other arm was used as the signalling arm, that they're going like this. And this arm hasn't moved at all. So there's a potent illusion of movement and displacement as a result of the vibration. And joint receptors don't do that. Joint receptors have other problems as well that make them unsuitable for mid-range position sensing. Because they respond at both extremes. They respond at the extreme extension and extreme flexion. But the observation that you could, muscle spindles are the only receptors in muscle that are highly vibration sensitive, that you could generate illusions of displacement and movement through vibration, was powerful evidence in support of muscle spindles as being the primary position sensors. So that was a really major step. It was Peter Matthews in Oxford who put that on the map. The contribution we made at Monash, I just wanted to talk about, it's a little bit complicated, is we studied a property of muscle which is called thixotropy. Thixotropy, is a common language term, is muscle memory. Thixotropy is a behaviour of the muscle that its property at any point in time depends to some extent on what's happened to it beforehand. I won't go too far into that, but what's interesting is that not only the ordinary muscle fibres have this property, but the intrafusal fibres, the spindles, have it too. So it's a means by which I can regulate, control the sensitivity of the receptor. And spindles are the only sensory receptors that show thixotropy. None of the others do.
How do you actually, how did you set up studies to actually measure that and look into what that did? Because that to me is interesting to be able to even study.
Yeah.
How do you actually set up an experiment?
Well, the answer to that is that there were some really bizarre experiments being carried on by people in various places trying to understand how the muscle spindle works. And one of the ideas that was about at that time was that perhaps there was some process of stretch activation. Stretch activation is, we have that in intestinal muscle. If you stretch the muscle, it contracts. And it was thought that perhaps muscle spindles did that as well. And of course that's wrong. but they do show thixotropy. And what's really interesting is that thixotropy produces characteristic patterns of muscle responses, and that is expressed in the position errors. If you thixotropically condition a muscle, I mean, we can go through it in detail, but the detail's a bit boring.
Maybe not.
The point that I'm trying to make is that muscle spindles produced errors of a particular pattern that was entirely consistent with the thixotropic behaviour of muscle in general.
The reason I say it's not boring is the fact that it, you know, like, I don't know if Jack explained this to you, but like I coach track and field at a high level, right? Like, I've had a few athletes go to the Olympics, the Commonwealth Games, stuff like that. And what this makes me think is if you consistently teach them the wrong thing, they're going to create these, as you said, these errors.
Yeah.
Right? So it's not boring because it tells you that what you actually teach people, what you get them to do in a clinical setting, what you get them to do in even a sports performance setting. If you're, as you said, thixotropically giving them the wrong information, they're going to have this property that's actually not conducive to the best performance of that condition. Yeah. So I think that's really interesting in it. Yeah. So if you want to, you can describe sort of how those things kind of develop.
Maybe I don't even want to because it's complicated. But what happens is it's essentially a property of passive muscle. Yep. That if what happens at the end of a contraction, there are some cross bridges between actin and myosin which reform spontaneously. And so the muscle fibre at the end of a contraction has a certain stiffness as a result of these bridges being attached. It's a spontaneous process. It needs calcium, and you know, people have made careers out of working all that out. Yeah. Well, what interests me is that once a fibre is stiff like that, if you then shorten the fibre, it isn't able to shorten itself because it's being held rigid by the bridges, and so it kinks. It goes slack. And that's a big feature of muscle spindles. So if you build slack into the muscle spindle, it's very low sensitivity. Its stretch response is weak, and the position signal is weak. If you tighten everything up by a contraction, then you have a much higher rate of activity and a much greater acuity, position acuity. So it is a way of manipulating the sensitivity of the receptor.
This makes me think of a couple of questions I want to ask you, and one of them is a question I sent you of how proprioception, or our position of a limb, is not just based on the position of that associated joint, but also other joints within the kinetic chain.
And the answer is yes.
And why is that the case?
I don't understand your why.
Well, it makes me, I think of what's actually regulating that. Why is it that when I bend my wrist, that the tension or proprioceptive signals being sent from that area of my body will also be dependent on where my elbow and my shoulder is in position? Yeah. Why is that? What is regulating that?
There is a map of the body in the brain, and signals from proprioceptors in all of the muscles are directed to that central map. And it's got to be a very complicated map because we make complicated movements. And you can get simultaneous input from whole groups of different muscles all being represented in the brain map of position of the limb. What we've done, we've just intentionally picked a really simple joint, the elbow joint, because it's much more difficult to interpret things that you see if it's a multiple joint situation. I got tangled up in that with gastrocnemius. You know, it acts both on the knee and on the ankle, and you don't always know where the link changes are coming from, so it's more difficult to deal with. Anyway, we studied the elbow joint for that reason, but it is a very complicated situation. An elaborate central map of all of the muscles, of all of the limbs, and the map must be sensitive to changes in activity in several locations simultaneously. Exactly how all that works out, I don't know.
Well, and this is something that I've thought about just because of my interest in the fascial system, and particularly the continuity of the myofascial system, because we start to see myofascial expansions, for instance, of the biceps into the antebrachial fascia. And that's a question I wanted to ask you of, when we think about regulating proprioception, is one of the things that regulates proprioception, say, in the forearm, based on tension created from, say, the biceps, because of the actual tension that's created through that fascial network, which would, again, would regulate tension within the muscle spindle itself? Is that something that...
Well, length and tension are closely related.
Yes.
So what we think the spindle does, it signals length. When you stretch the muscle, the spindle is stretched. When you shorten the muscle, the spindle goes slack and it goes silent. So we basically think it's a length receptor. We have also, of course, got tendon organs, which are sensors that are specifically designed to sense tension in the muscle as well. So you're right, but there are several sources of this stuff. Yeah.
So I know one of the other papers that you've published, I think this is actually more of a literature review of looking at how we lose proprioception in a weightless environment. So I know there's been studies of, say, being underwater.
Well, you saw that, did you?
I did. And I find that very fascinating because it highlights what you're saying here too, of that tension or length is something that regulates our ability to determine where we are in space. Yeah. And if we lose that, we start to see an inability to regulate or know where we are.
All right. Let me tell you what we are thinking about right at this present time. I've written a draft manuscript, but we need to do some crucial experiments. Are we still all right?
Yeah, we're good.
Absolutely.
Yeah, good to go, man.
So what we did was, one of the problems with proprioception is everybody measures it differently. So you get lots of different outcomes and you don't really know how to compare them because the methods are so different. So we were studying different methods of measurement of proprioception, and one method that we used was to place an arm behind a screen so that you can't see the arm, and the other arm pointed to locations where you felt the arm was behind the screen. I've simplified it, but you get the idea. There's a big screen. We often have an eye patch on that side, so you can't see anything on that side. And the arm's here. There's a potentiometer here for angle measurement. There are 4 sensors, and you move the arm, and you ask the subject to point to where they think the arm is. And they're quite good. They're quite good at that. And we did that experiment, and what we found was, and the apparatus is pretty good. We measured from 90 degrees down to full extension. What we found was that subjects knew where their arm was with pretty good accuracy in the mid-range. When I say pretty good accuracy, there were errors, but it was reasonably accurate. But when the arm was moved more and more into extension, the errors became smaller and smaller, and close to full extension there were no errors at all. So something is changing with position sense as the arm is moving close to its limit. And the obvious answer is this is where you're beginning to engage the joint receptors. So the idea we've now got is, I mean, people have always said joint receptors are sort of limit receptors, they're handbrakes, so that when you get towards the limit you don't damage the joint because of their signals, and that's all true. What our view now is that the joint signals are more mixed. There are 2 sources of position coming. There's the spindle signal, which continues right into the full extension, but here you also have joint input, and the 2 are combined within the brain to give you an accurate position sense in relation to the 2 limits of movement of the arm. And that's new. That's a new idea. So that we now have 2 proprioceptors of quite different origins, and there is evidence that each of them is represented in the brain in a different location. So the spindle signal goes to one site, the joint receptor goes to a different site, and somewhere in the brain those two signals are combined into a true position sense.
More accuracy,
yes,
as
correct. That's correct. That's correct.
Yeah.
That's correct. That's correct.
That's quite interesting, because that opens up a lot of different chains of thought around. Straight away, I go into the clinical mode of thinking about, like, what does that mean for how you expose people to different stimuli, and maybe what that means for developing those proprioceptive things, say in a rehabilitative sense, particularly for someone, say, post-surgery, who's probably had tissue actually been cut and changed, and they've got different sensory information because of swelling or all sorts of different things. What do you need to expose them to? And it even makes me think, Jack, of like stretching, and how you probably need to find different types of, not modalities, but, different lengths to work at to give some of this different information at different times.
Yeah, absolutely.
It's pretty interesting, really.
That's really interesting.
It just fell out. We kept making these arm measurements, and subjects got incredibly accurate towards the limit, and it didn't make any sense, no obvious sense.
How long ago did you do that?
It is ongoing. We've just recruited a new student for next year who's going to be working on this.
Fantastic.
What we haven't done yet is this. We haven't done full flexion. We've done full extension. The same thing should happen at both limits.
Why do we lose proprioceptive ability after intense exercise?
Hang on, before we go to that,
all right.
What you brought up before was what triggered me to tell you this recent story, was weightlessness.
Yes.
And so what we're going to have to think about now in terms of understanding weightlessness is that as the arm is extended, the weight of the arm bears down on the elbow joint, and that will probably sensitise the joint receptors into activity. But if you're in a weightless environment, you eliminate the joint receptor signal. And that, in my opinion, that has an impact on the whole position sense signal. There's some interesting stories from astronauts. This guy lying in the dark in the capsule in flight, and he sees this luminous dial in front of him, and then he switches the light on, and of course it's the dial of his watch on his arm. He's completely lost his sense of arm.
Where his arm is,
absolutely. He's lost the sense position of the arm.
With this experiment you described before with extending the elbow, was this done in a passive position where, or were they? Okay.
Yes.
Yeah.
It's good point. What we're going to do next is to load the arm. Because the joint receptors are within the joint capsule, and these are Ruffini endings that attach to the wall of the capsule, and distortion of the capsule produces responses. And the idea is that if you impose a force on the joint, that will distort the capsule, and that will lead to a response from the receptors. And if you in a weightless condition, there is there's no load on the capsule, and so you don't have that input.
I'm interested to hear your perspective then of thinking about this clinically. You're probably aware that in physiotherapy or in a lot of type of rehabilitation settings, they'll use things like wobble boards or unstable surfaces like standing on a foam mat to quote unquote challenge your balance. And you can appreciate that at that very single joint level there's going to be a lot of altered input, and therefore you have to be able to regulate to keep your centre of gravity over your base of support. Do you think that will get a good translation to doing more dynamic, high-velocity tasks, like something like change of direction, which when you think about from an injury perspective is a high-risk type of movement for things like knee injuries? Do you think that we get a good transfer of doing unstable training to that type of task, or do you think we need to have much more specificity with the movement in order to build proprioception?
I can't really answer that. I'm not sure. What I would say is, to your earlier question, if you want to maintain your proprioceptive system in full working order, use it. So, a thing like doing up a button on the shirt Find the manipulative tasks that are demanding. You should, particularly older people, should repeat doing those and struggle through them, because it will help proprioception. And
also, but then thinking about, does that task require multiple joints? What's the speed of that task itself too? To think about...
I haven't done anything like that. Okay. Whether or not there's information on it, I don't know. But you then also asked about exercise and proprioception. And we worked on this for some years, and it's a little bit complicated, but after exercise it reduces the maximum voluntary strength by about 20 to 30%, exercise a particular muscle. You do see errors. At the forearm you see errors into extension. At the knee you see errors into flexion. I don't have any idea what the significance of that is. And what we had, when you go into these things, you have naive ideas to begin with. We thought maybe after intense exercises, chemical products, lactate or anything that's affecting the spindle, or maybe there's some sort of... And I should say the exercise can be concentric or eccentric or isometric. All of them do it. And our finding is it's not a question of damage from eccentric exercise. The spindles seem to be resilient. They don't seem to be damaged. And that's probably due to connective tissue. Anyway, I've lost myself now. But the exercise leads at the forearm into perception that the arm is more extended than it actually is. We thought, well, that might mean that the spindle is discharging a bit more vigorously because it's a bit damaged. But it cannot be that, because we, at one stage, exercised biceps, and then we exercised triceps. Biceps exercising is you lift a weight, it's easy. What we did with triceps was we had a pulley behind the head and to a weight that's hanging behind the person, and they had to lift up the weight. And in the process, they were, no, maybe lower it down.
I can't remember. Pushing down,
yeah, pushing down. So we were exercising the triceps, elbow extensors. And it was the outcome of that experiment was also a perception of the arm as more extended. So there, more extended for triceps means a shorter muscle. More extended for biceps means a longer muscle. Doesn't make sense. None of that makes sense.
Here's a question you might not have an answer for, but it would be worth to get your opinion. Is what evolutionary sense do you think that makes, that after, say, intense exercise, we do lose some of that ability? Do you think that there's anything to read into that? Why would we have evolved to actually have that change?
Well, I can't remember off the top of my head how big the errors were. They were something of the order of, say, 5 degrees. That can produce sports injuries. If the guy doesn't precisely know where his foot is,
thinks it's a
because the proprioception is misleading him, it can potentially lead to injuries, for sure. So it's an important topic. But there's something really strange going on. I think it's to do with the fatigue and perhaps the sense of effort, but it's all going on in the brain. How can the arm always be perceived as extended, regardless of whether you fatigue biceps or fatigue triceps? We should have got a different result for triceps. The fact that we didn't is bizarre. And I don't know. I don't know. It needs further study. It's an interesting area.
Do you think part of that is regulation of proprioception is based on input both from the agonist and antagonist plane?
Absolutely.
So you actually have to have that feedback to go.
Absolutely.
Okay.
It's not only that in position sense in position matching. It's the proprioceptive signals from both arms. So if you blindfold it and you have this arm here and this one here, we know that the brain is listening to this and it's listening to this and it's combining them. We know that. And it's really fun, because if you use thixotropy and you produce thixotropic errors, they'll show up because of the direct match between the proprioceptive signals of the two arms. So yes, it's not just flexors and extensors; it's also the two arms as well. On the other hand, if you have this arm out here and you try and match the angle of the arm here against that, that's seriously inferior.
Yeah, and again, that to me just really highlights that when we think of something like proprioception, there's a lot of input, because what you're changing there is, in thinking about the shoulder,
indeed,
you're changing a plane, and therefore tension within a different plane of the arm. And so, like, for me, that sort of reinforces from a rehabilitation principle. If we think about developing proprioceptive capacity, we need to have that specificity of movement. It's like think of someone like a cricket bowler or a baseball pitcher. There's so much complexity in their movement in terms of not just what's happening at the wrist, elbow, shoulder, but then even tension through that whole anterior chain of the arm down into the leg. So, you wouldn't get a baseball pitcher just to do this all day to build proprioception of their ability to throw a ball. You need to actually replicate that whole movement, and therefore tension within that myofascial chain, and therefore the proprioceptive input that occurs from that.
But it is still interesting to know, quite apart from the fact that shoulders involved, that reproducing this angle here, out here, is grossly inferior. We don't have that ability because we don't use it. What we do is we put our arms together, the hands facing each other, and we manipulate objects. We make tools, we fiddle with things, and that posture is crucial. And the brain's organised in that way. It looks at both hands, both arms, and it's constantly comparing the proprioceptive signals from both.
I think of that even too just with everyday tasks. If you go to pick up a cup, you're thinking about getting your hand into a position to pick up the cup. You don't think about where your elbow or your shoulder is.
No, it's all integrated.
Completely, like it's just at a subconscious level knowing, well, I need to put my arm and my trunk in this position in order to be able to manipulate my hand in space.
And one other thing in measuring proprioception, which I should mention, is the clinicians often use what they call a repositioning method. So the way you do that is subject's blindfolded, the arms put out to a particular angle, and then the experimenter says, remember that, and so then the arm's brought back again, and then the subject has to reproduce that angle. And so that they've learned a proprioceptive signal, and they're very good. They're very good at the errors are small, amazing. But it's different. It's different to this. This is where the brain is constantly matching the two arms. It's ongoing. In a memory task, there must be some I don't know, some memory component that's sitting there, having learned that particular angle to be able to reproduce it.
It's almost like there's a shadow left in the brain somewhere that it kind of recalls a bit of, over time that dissipates.
Is that why you have things like phantom limb pain then too?
Yes, well...
Who knows?
Yes. I of course don't understand phantom limb pain. I mean, it's again, it's a brain issue. Just thinking about it, it probably doesn't in the first instance involve proprioceptors. Certainly not the pain, not directly. And what you do is you use mirror therapy to alleviate it.
Yes.
And that works very well. But you're basically tricking the person into believing that the left arm is the right arm. That's the mirror therapy. These are things that are going on in the brain that I that's out of my depth. Yep. How are we going?
Well, we're about to hit an hour, so I think we're going pretty well.
Okay.
There's one, you've already mentioned a few different things, but I think there's one question that I've been asking pretty much all of our guests that I think like yourself, and I think it's probably a bit more impressive coming from yourself. You're a bit older now, but you still seem to maintain a huge amount of curiosity. I find the curious people are always, tinkering with different problems, whether they be on the surface or, deep in their brain somewhere. Are there any ideas that at the moment you're still tinkering with that you would love to know the answer to over this next period?
I'm very, very keen on this joint receptor thing because that will revise proprioception. So the new dogma will be, no, you're not just dealing with muscle spindles, you're dealing with a combination, and that will change. That will change the view that we have. Let me tell you about that a little bit. People have vibrated. You knew that vibration produces illusions, but if you vibrate biceps and at the same time extend the arm, and extending the arm will sensitize the muscle because everything's getting tighter, so the vibration is transmitted more completely, then people get to the point where they report a hyperextended arm. So they report that they tell you, this vibration's going on, and they say, my arm is down now in a hyperextended position. And you can do it with flexion as well, with triceps. So muscle spindle signals don't have any limit. They don't have any end point. They will continue to signal, and the brain interprets a stronger vibration signal as a longer muscle, even though it's anatomically impossible. The limiting signal is the joint signal. That increases until you get to the anatomical limit. You can get, if you force the joint a little bit into beyond its limit, what the joint receptor does is it maintains its rate or it begins to fall. So it's clearly signalling the anatomical limit, and that information is transposed onto the spindle signal to produce a combined position signal. I just think it's amazing. It's amazing.
Something I've read about is thinking of the significance of retinaculum, because if you look at an anatomical textbook and you look at the retinaculum around any joint, particularly the wrists and the ankles, they're typically just noted to hold tendons in place. Yet I know there's been more studies of looking at, are there actual receptors, mechanoreceptors in there? I know that there's been some more recent literature of looking at, they're very highly innervated with Pacini and Ruffini corpuscles. Are you familiar with any of this research? And if so, do you think retinaculum have an important component in proprioception?
I don't know anything about retinaculum. Okay. I'm been interested in vibration. A couple of things. The fingertips are full of Paxinian corpuscles, and you can see when a person is reading Braille, the undulations of the surface are being signalled really faithfully. And whenever we touch a material and measure and assess its texture, things like the rapidly adapting receptors are crucial. So they're pretty important. And in animals as well. Snakes have vibration receptors all along their length, and they can detect the approach of ground-born predators through ground-born vibration. I haven't really answered your question.
That's okay. No, it's something that I'm interested to explore more, because I know, particularly looking at, say, like ankle injuries, we have some very important retinaculum around the ankle, the flexor, peroneal, extensor retinaculum. And in looking at individuals with chronic ankle instability, one thing that can be evident is disruption of the retinaculum as well, and how that potentially alters sensory input, in addition to, say, obviously some of the ligamental structures.
May well be so. Yes, I don't know. No, it's not something I've worked on.
Yeah. Okay.
Yeah.
Alrighty, I think we might wrap it up there, but thank you very much, Uwe. We really appreciate you taking the time. It's been a very interesting and insightful talk. I think you've educated us much more than we've elucidated much for you, but thank you so much, and we really appreciate your time.
It was a pleasure to come here, John.
Thank you, Uwe.